presence of oxygen. Remember the glucose chemical structure, it was C6H12O6. And remember, in order for me to break this down and to yield the maximum amount of energy, I will need to have oxygen. So this reaction requires the presence of oxygen. Breaking down the glucose in the presence of oxygen is a multi-reaction process. Remember, this will result in the formation of carbon dioxide, water, and it's going to be yielding around 32 ATPs plus some of the energy released is going to be in the form of heat. So if you remember, we mentioned last time that one molecule of oxygen is going to be yielding between 32 to 36, and in some cases 38 ATPs. Remember, in order for us to break down the glucose needs first to enter the cell. So if I have my glucose outside in the blood, here, this glucose needs to travel to the inside of the cell in order to be broken down. If this is the cell membrane on here. In order for me to do so, remember, I need to have insulin, which is a hormone that enhances the cell to uptake the glucose. And on the surface of the cell, I need to have a surface receptor for the insulin to be present and functioning normally. And those two components are going to be the two reasons for the two different diabetes mellitus. So in type 1 diabetes, what's going to be my problem? In type 1, I have an autoimmune disease that causes the destruction of the islets of Langerhans in the pancreas, so I'm not able to produce insulin. In type 2, I have a problem with the receptors. The receptors are not functioning normally, so even in the presence of insulin, I don't have normal functioning receptors to induce the action of the insulin inside the cell. Remember, the insulin, when it binds to its receptor, it induces the cells to produce carriers or transporters that will allow the glucose to the inside of the cell. And we call those are the glucose transporters or GLUT. We have different types of glucose transporters according to the type of cells that we're dealing with, and each one is going to be allowing the glucose to pass to the inside of the cell according to its level outside in the extracellular fluid. So for example, the fat cells will have a much higher glucose levels in order for them to form their glucose transporters. So I need to have much greater levels of glucose outside in the blood for this extra glucose to be picked up into my cells. Compared to the brain cells, I can form the glucose transporters and much lower blood glucose levels. So at the end, whatever is the type of the cells that we're dealing with, this glucose gonna be traveling to the inside of the cytoplasm. So I've got now the glucose from my blood to the inside of the cell. Now the glucose is located in my cytosol, the part of the cytoplasm without organelles. And this glucose needs to be broken down. And the first step of the breakdown of the glucose is what we've called the glycolysis, in which I am breaking down the glucose without oxygen into two pyruvic acids, or 2-pyruvate. This reaction yields a net energy gain of 2 ATP. Why do we say net energy gain? Because simply when you are discussing this reaction in biochemistry, they will teach you that you're actually going to be getting 4 ATPs out, but you need to get 2 ATPs in order for the reactions of the glycolysis to take place. So at the end, you're going to be yielding 2 ATPs. This is your net gains from the glycolysis. Also, in this reaction, you're going to be losing 2 hydrogens. And remember, the hydrogens are going to be attached to hydrogen carriers. So the hydrogen here is going to be carried on a hydrogen carrier called NADH. So you've got 2 hydrogens lost here. So remember, the glucose that we started with did have 6 carbons and 12 hydrogens. So those 2 pyruvate, after I lose 2 hydrogens from the glucose, and I splitted the glucose into 2 pyruvic acids, this means what for me? This means that each of the pyruvate gonna still have 5 hydrogens and 3 carbons. You've got 2 of them, remember. You've got 2 pyruvic acids. In order for me to break down the pyruvic acid, I need to have oxygen and I need to pass through a cascade of chemical reactions. We call the cascade of chemical reactions, it's the Krebs cycle or the citric acid cycle. And this takes place inside of the inner membrane of the mitochondria. Remember, here I was inside the cytoplasm. Here I will be inside the inner membrane of the mitochondria. Remember, the mitochondria did have 2 membranes, an outer membrane and an inner membrane. We're looking here at just part of one mitochondria, which is the organelle, again, responsible for the formation of energy. It is the powerhouse of the cell. The first step, the initial step, in order to process the pyruvate is to transform it into acetyl-CoA. While you are transforming each of those 2 pyruvates into acetyl-CoA, you're gonna be losing a carbon. So you see on here, each of those pyruvates will be losing a carbon. So now the acetyl-CoA gonna only have 2 carbons remaining. Also, in this step, when you are transforming the pyruvate into acetyl-CoA, you're gonna be losing a hydrogen. Attached to a hydrogen carrier, NAD. So now the acetyl-CoA You're gonna have 2 carbons, but how many hydrogens after I lose? So remember, pyruvate did have 5. So when I lose 1, how many hydrogens are still gonna remain in the structure of my acetyl-CoA? Did have 5, I lost 1, so I still have any other ideas? 4, exactly. 4 hydrogen. So how many acetyl-CoA do you have from a glucose? What we're concerned here with is the breakdown of the glucose. So you did split the glucose into 2 pyruvates. Each pyruvate is going to be transformed into acetyl-CoA. So how many acetyl-CoAs would you have per glucose? 2. I've got 2 acetyl-CoA that are going to be formed from each glucose. The acetyl-CoA will pass through a cascade of reactions. Remember the very basic concept that we've talked about last class? If I told you that in order for me to pass through this cascade of reactions, I will be adding something called the oxaloacetate or oxaloacetic acid to the acetyl-CoA. And from this reaction, you're going to be forming citric acid or citrate. That's why we call this cycle the citric acid cycle or citrate cycle. So this citric acid, it's going to be passing through multi-reaction process, many reactions. We don't need to know the details and the intermediates of those reactions to become oxaloacetate. Again, so if I'm becoming oxaloacetate again, this means that throughout those reactions, what did I lose? If I'm telling you, you have a reaction, X plus Y equals Z. And then I told you that Z will become Y. So in order for me to become just Y, what do I need to lose? So in other words, Z equals Y. So you have to subtract from the Z, ZX. So Z minus X equals Y. So who is the Y here? It's going to be the oxaloacetate. Who's going to be the X is my acetyl-CoA. Who's going to be the Z is going to be the citrate. So I'm telling you that the citrate will become oxaloacetate, will become the Y. So I need to subtract the X. So I'm losing the X. I'm losing the acetyl-CoA. This is what I will be losing through this cascade of reactions. So what will I be losing? I will be losing the carbons in the form of carbon dioxide. I would be losing my hydrogens, and how many hydrogens did I have again? Can you remind me? In each acetyl-CoA, I have 4. Exactly, 4. So you've got 4 in each acetyl-CoA. So you're gonna be losing 4 of your hydrogens. 3 of them gonna be carried on a carrier called an AD, like the ones that we've used before. So you've got 3 NADH. So if I'm losing 3 of the 4 attached to NADH, I still have 1 more to lose. So this is gonna be lost, carried on another hydrogen carrier called FADH. And through this process, I'm also breaking down. We didn't mention the details of those reactions. In those reactions, I will be breaking a high energy bond. And remember, energy can't be created and can be destroyed. Energy gets transformed from one shape to another. All right, so in this cascade of reactions, while I'm breaking down the oxaloacetate, while I'm breaking down the citrate to become oxaloacetate, losing the components of the acetyl-CoA in the process, I'm breaking down a high energy bond. And remember, this energy can't be destroyed. So it gets transformed. So how would I transform it? I will rebuild another high energy bond that would be created between an ADP and an inorganic phosphate, producing an ATP. So from each Krebs cycle, from each citric acid cycle, this is a Krebs cycle here. Starting from the pyruvate all the way to get the carbon dioxide. All right, so here I did gain 1 ATP. I did release 4 hydrogens, attached 3 of them to an AD, and 1 of them attached to an FAD. Again, where did you get those 4 hydrogens? Remember, glucose did have 12. You've lost 2. Each pyruvate gonna have 5. When you transform the pyruvate into acetyl-CoA, you're gonna be losing 1. So now in each acetyl-CoA, you have 4 hydrogens remaining and 2 carbons. The acetyl-CoA gonna be broken down through a cascade of reactions. And those reactions, in order to take place, you need to attach the oxaloacetate to acetyl-CoA and form citrate. When you are transforming the citrate into the oxaloacetate, this is going to result in production of ATP, release of 4 hydrogens. Right. How many acetyl-CoA do I have from each glucose? How many acetyl-CoA do I have from each glucose? 2, right? So how many ATPs will result from the Krebs cycle from a glucose? How many ATPs will result from breaking down a glucose, not an acetyl-CoA? In acetyl-CoA, it's going to be 1, right? But you have 2 acetyl-CoA, so you have 2 Krebs cycles. And if you have 2 Krebs cycles, this means that you're going to be producing 2 ATPs, right? From a glucose. And how many NADH would you be releasing from each acetyl-CoA again? You're producing 3. So how many would you get from each glucose? 6 from those reactions. And remember, you've got here 1. So in the transformation of the NAD as the pyruvate to acetyl-CoA, you're going to be also releasing 1. So you've got 2 here and 6 in here. I need to review this for us. I'm sorry, I did have a mistake in here. So 5, 6. I need to recount this. All right, yes, we're correct. We're right. All right, so again, I've lost 2 hydrogens while I'm transforming the pyruvate into acetyl-CoA. I've lost 6 hydrogens when I'm transforming the 2 acetyl-CoA, when I'm breaking down the 2 acetyl-CoA in the Krebs cycle. So how many NADHs did I produce from each of the glucose so far? So you've got here, from the glycolysis, you have released 2. From the glycolysis, you've got 2 NADH. And from the Krebs cycle, including the transformation here, I got stuck. Including the transformation of the pyruvate into acetyl-CoA, you've got 2 plus 6. So you've got 8 NADHs that you get released from the Krebs cycle. So you've got 8 NADHs. And remember, you're also going to be losing an Fe and a hydrogen, but this time was attached to an FED. So you're going to be releasing from the Krebs cycle 2 hydrogens attached to FED. You've got FED, 2 of them. So I need to exit here the screen for a second. Here we go. All right, so again, what we're looking at in here, we are looking at how many hydrogens did we lose. We know that we're gonna be losing 12 hydrogens because those are the this is gonna be the number of hydrogens present in a glucose. So you've got 2 lost during the glycolysis when you are breaking down the glucose into 2 pyruvate. You've got 8 lost attached to NAD, and you've got 2 lost attached to FAD. How many ATPs did I get from all those reactions? I've got 2 ATPs from the Krebs cycle. I've got 2 ATPs from the glycolysis. So I have a net gain so far of 4 ATPs. Remember, a glucose is supposed to yield 32 ATPs. So we're looking on here. How would I be using those high energy bonds between the hydrogen and the hydrogen carriers to allow the formation of ATP? Remember, this will take us to another cascade of reactions. We call this is the electron transport chain that will be taking place inside the mitochondria. And this is the main part that yields the maximum amount of energy. Remember, I've got the NADH on here. I've got the FADH. Those are high energy bonds between the carriers and the hydrogen. I need to split the attachment here between the hydrogen and its carrier. I need to split the attachment between the hydrogen and its carrier, like this. This will free the carrier and allow it to get more hydrogen that will be released from the Krebs cycle from the glycolysis. So I'm freeing the carrier. And this hydrogen will be allowed to travel from the inside of the inner membrane of the mitochondria to the intermembrane space. So you're gonna have a lot of protons accumulated here. Those are high energy electrons and protons. All right, I don't want to get involved in the details of the process. All right, just keep it simple. So you're accumulating those protons on here in the intermembrane space, in the space between the inner and the outer membrane of the mitochondria. This creates a very high potential energy for the protons. So they were always going to be trying to move from the intermembrane space where I have a very high concentration of them to the inside of the inner membrane where I have very low concentration of those protons. So they are trying to move in. This is what creates this high potential energy. In order for me to use this energy, what I will do, I will allow them to travel, but as they are traveling, they will be losing this potential energy, and this what allows the transporter on here called the ATP synthase to use this energy and to build up ATPs. I'm using the energy to build up a high energy bond between an ADP and an inorganic phosphate, producing ATPs. This is how do I generate ATP from the hydrogen attached to the hydrogen carriers in a very simple way. But remember, in order to allow those hydrogens to keep traveling down their concentration gradient, losing their potential energy, in order for me to build up those ATPs, I need to keep a very low concentration on the inside of the inner membrane. So this hydrogen needs to be attached to oxygen. So all the time you're going to be binding this hydrogen to the oxygen that you're breathing in order to form water. And this is the metabolic water that we have been talking about. The water that gets produced as a byproduct of the metabolic reactions. Why, if I stopped breathing, my cells cannot survive? Because simply, in order to carry on all the cellular metabolic activities, you're gonna need energy. And how do you produce the largest amount of energy in your cells? By breaking down the nutrients, including the glucose, and this will allow you to form high energy bonds between the hydrogen and the hydrogen carriers that you're gonna use through the third step on here of the breakdown of the glucose. It's called the electron transport chain. It's a chain of carriers that you're going to be passing through that we're not discussing. That's why it's called the electron transport chain. So if I stop breathing, why my cells can't function? Because they won't have this oxygen. And if they don't have this oxygen, those protons gonna build up on the inside of the inner membrane and will be preventing any further influx of the protons from the intermembrane space to the inside of the inner membrane. If I have equal concentration on both sides of the membrane, this means that those hydrogens will not be traveling to the inside of the inner membrane anymore, so they will not be passing through the ATP synthase, and as a result, the ATP synthase will not be able to produce any more ATPs. Does this make sense? Does this make sense? All right, great. So where did I get the 32 ATPs? Remember, I had a net gain of 4 ATPs. Where did they came from? 2 of them are coming from the glycolysis, the very first step. I've got 2 from the Krebs cycle. So I've got 4 ATPs before I get into the electron transport chain, before I use the hydrogen attached to the hydrogen carriers. So how many NADH do I form from both the glycolysis and the Krebs cycle? Remember, you've got here 2 and 8. So you've got 10 NADH. And how many FADH did I have? I've got 1 that will be released from each Krebs cycle. So this means I have got 2 Krebs cycles, so I will be forming 2 FADH. per glucose. All right, so what is the number of ATPs that we're going to be producing here? From each NADH as it travels through the electron transport chain. Each NADH going to be yielding, passing through the electron transport chain, it's going to be yielding 2.5 ATPs. And each FADH going to be yielding 1.5 ATP. So can you calculate this for me? We've got 10 NADH, each one is worth 2.5 ATPs. And 2 FADH, each one is going to be yielding 1.5 ATP. So 10 times 2.5 equals to 25. And 2 times 1.5 equals 3. And how many net ATPs did I produce from the glycolysis and the Krebs cycle before the electron transport chain, before I break down the hydrogen from their hydrogen carriers? I've got 4. So can you add this together? This is going to be equal to 32 ATPs. Which is going to be the initial number of ATPs that we've mentioned at the beginning of the reaction. Any questions? Any questions? Anything that doesn't make sense so far? All right, great. All right, so let's read this part from your handouts. So the oxidation of the glucose is going to be a 3-step process. First, we're going to be starting with the glycolysis. Then we got the Krebs cycle. And the third step is going to be the electron transport chain, which is going to be followed by the oxidative phosphorylation. From the glycolysis, you're going to be transforming the glucose into 2 pyruvic acids. This yields a 2 ATP by breaking down a high energy bond. Also, this pyruvate, as it travels to the inside of the inner membrane of the mitochondria, passing through the Krebs cycle, gonna give you a net gain of 2 ATPs. The NADH, FADH that you did accumulate from the previous reactions going to be passing through the electron transport chain, which is going to end up allowing oxidative phosphorylation to take place. And this will allow you to produce ATPs 2.5 from each NADH and 1.5 from each FADH. First step is the glycolysis. This is going to be forming 2 pyruvic acids. What if I don't have oxygen I won't be able to get the pyruvate to be transformed into acetyl-CoA and travels to the inside of the inner membrane of the mitochondria, but it's going to be transformed into lactic acid. If I don't have oxygen, the whole process is going to be stopped, and the pyruvate, as it accumulates in the cells, it will be transformed into lactic acid instead of acetyl-CoA. If I have oxygen, if I do have oxygen, this will take me to the aerobic pathway. This reaction going to be releasing two hydrogens attached to two NADH and yields two ATPs. Second phase of the breakdown of the glucose is going to be taking place inside the mitochondrial matrix, on the inside of the inner membrane of the mitochondria. It's going to be filled up by the pyruvic acid, and as we're going to see also by fatty acids that have the ability to transform into acetyl-CoA. Each pyruvic acid is going to be converted into acetyl-CoA, and the acetyl-CoA going to be shuttling through the multi-enzyme cascade of reactions called the Krebs cycle. Through the Krebs cycle, I would be releasing 6 carbon dioxide, 8 NADH, and 2 FADH. So again, those numbers are for 2 Krebs cycles. Remember, I've got 2 Krebs cycles per glucose. Those numbers are for each glucose, not per Krebs cycle. And the same concept here for the 2 ATPs. For each Krebs cycle, you're going to be releasing 1 ATP, but you get 2 Krebs cycle for the glucose. So this is going to yield 2 ATPs. Again, the most important step for us, and the only important step for us actually, is going to be the one that initiates this cascade of reactions, which is the attachment of the acetyl-CoA with the oxaloacetate to produce the citric acid. And what you simply need to know is that the citric acid, as it travels through this multi-step reaction, it's going to become oxaloacetate another time, and during this process, you're going to be losing all the components of the acetyl-CoA. This takes us to the electron transport chain and oxidative phosphorylation, which is a part of the metabolism that requires the presence of oxygen to take place. You're gonna start the electron transport chain by having the hydrogen attached to their hydrogen carriers. The energy is going to be transported from the hydrogen to the oxygen, releasing large amounts of energy. And this energy is released in a stepwise manner through the electron transport chain. As we mentioned here, you start by having the hydrogen carriers. You're going to be splitting the proton away, allowing the protons to accumulate between the 2 membranes of the mitochondria, creating a very high potential energy. And in order for me to use this potential energy, I will allow the protons to travel from the intermembrane space to the inside of the inner membrane, to the matrix of the mitochondria. This transport of the protons from outside to the inside of the mitochondrial matrix is what allows the rotational movement of the ATP synthase that allows you to build a high energy bond between the ADP and the inorganic phosphate, producing the ATP. Again, why did I call it oxidative phosphorylation? Remember, what is phosphorylation? It's the addition of phosphate group to a structure, a chemical compound. So here I'm forming a phosphorylation reaction. But in the same time, this phosphorylation will not be taking place if this hydrogen did not bind to an oxygen, remember? Because you're gonna need to keep the protons traveling inside. So you're gonna be adding oxygen, which is an oxidative reaction. So what do we call those together? Those reactions, the addition of a phosphate group to an ADP and the attachment of the protons to oxygen. We call those two together oxidative phosphorylation. And remember, again, each NADH is going to be yielding 2.5 ATPs. Each FADH is going to be yielding 1.5 ATP. This gives a total of 28 ATPs that will be produced from the electron transport chain and oxidative phosphorylation, plus 2 that you have released from the Krebs cycle, and 2 ATPs that were released from the glycolysis. This will give you about 32 ATPs. Why we say about 32 ATPs? Remember, because not all the energy here, or not all this potential energy, gonna be transformed into ATP. For example, a hormone called the thyroid hormone. If you remember, it's a calorigenic hormone. What I mean by calorigenic hormone, it's going to be responsible to produce heat. So one of the actions of the thyroid hormone is going to be to uncouple those two reactions. So I'm allowing the hydrogen to travel in, but without the production of ATP. So again, energy can be created or destroyed, remember? So this energy needs to be transformed into another form. And what is the other form? If I didn't use this potential energy to produce ATP, it's gonna be generated as heat. So normally this takes place all the time, that some of the protons will travel and they will not be allowing phosphorylation of ADP to take place. This is what's going to be producing heat. Some drugs, some hormones also will be increasing the uncoupling here allowing the protons to travel without the production of ATP. This means I would be producing much more heat. Like the thyroid hormone, it's a calorigenic hormone. Moving on to the energy reserves. When cellular ATP reserves are high, the glucose catabolism is going to be inhibited. So if I have a lot of ATP, you're going to be inhibiting glycolysis. You're going to be inhibiting the transformation of the pyruvate into acetyl-CoA. This means that you're going to be stopping all the Krebs cycle, all the electron transport chain, all the oxidative phosphorylation. All this is going to stop. If you do have a lot of ATP in your cells, you don't need more ATPs in your cells. So what's going to happen? You're going to be blocking all the previously discussed reactions. And you're going to be inducing more of the anabolic reactions. You're going to be transforming this glucose that you've taken into its storage form, which is the glycogen. I'm converting the glucose that I'm not going to be in need to break down right now, and I will store it in the form of glycogen. And we call this process of the transformation of the glucose into glycogen is the glycogenesis. Glycogen, I am the storage form of the glucose. Genesis is the creation or the formation. So the creation of the glycogen from a glucose, it's called the glycogenesis. Also, your body tends to store the extra energy in the form of fat, triglycerides, inside your adipose tissue cells. We call this process is lipids, fat, genesis, creation or formation. So again, if you have more intakes than what you need, you're gonna have higher ATP reserves in your cells, and the higher ATP reserves will be inducing the anabolic reactions. You're building up more complex structures from the glucose. This includes the glycogenesis and the lipogenesis. Glycogenesis is going to be mostly taking place in the liver and skeletal muscles, but your body tends to produce more fat than glycogen. So if you eat a chocolate bar that you don't burn, so most likely the carbs in this chocolate bar are going to be transformed into stored fat in your adipose tissue cells rather than stored glycogen in your muscle and liver cells. So I tend to store much more fat than glycogen because you have almost an unlimited space to store fat compared to the glycogen. You have very limited space to store the glycogen. In your muscles, you're gonna have the contractile myofilaments, you have the myosin, you have the connective tissue, you have a lot going on inside your muscles compared to your fat cells. Fat cells are large vacuolated cells that contain nothing except for the stored fat. So if we're looking here, why your body tends to store more fat than glycogen, because you have much more space to store the fat than you do have for the glycogen. What if I have low blood glucose level? I didn't eat anything today, would I be able to function normally? Remember, your brain needs continuous supply of oxygen and glucose. It needs glucose supply all the time because it has a very high metabolic rate. So what will I do if I have this drop in my blood sugar level? First, you're going to be converting the glycogen stored in your liver cells and your skeletal muscle cells into glucose, which is much easier to break down. See on here, when you start to break down, you start breaking down the glycogen. It's much easier than the fat. After that, which takes longer to process, you're going to be breaking down the fats and proteins. So you're going to go to your skeletal muscles. You're going to be breaking down your skeletal muscles. You're going to go to your adipose tissue cells, and you're going to be breaking down the fats stored inside. That's why, what do we recommend for people who are trying to lose weight? To not just starve yourself. Get enough intake of proteins. Exercise. What we're trying to do here is to keep the muscle bulk, to not have a reduction in the muscle bulk. But if I'm not getting enough protein intake and I'm starving myself, I'm not exercising, I'm not doing anything except for starving myself, what will I end up with? I will end up losing both the fat and also the muscles. You're going to be transforming the amino acids that build up your proteins, the triglycerides that build up your stored fat, into glucose. So you see on here, I'm using a non-carbohydrate source to get the glucose. We call this is the gluconeogenesis. Why gluconeogenesis? Genesis again is to create or to form, to produce. And gluco here, I mean by the gluco is the glucose. So I'm producing glucose. And what I mean by neo means new. So this is a new glucose that I'm producing. Why is it new? Because simply it hasn't been a carbohydrate before. Unlike this one from the glycogen. So what is the structure of the glycogen? It is simply glucose attached in chains to one another. So what you do in the glycogen in the glycogenolysis, the breakdown of the glycogen, you're gonna be separating the glucose from one another. So it has been a glucose before. It was just attached to another glucose to form the glycogen. So it's not something new that I'm getting. It's already present as a glucose in a stored form. It's packed together. It's not something that I've created. But here, this is something that I've just created from the fats and the proteins. It has a non-carbohydrate source. That's why we call it gluconeogenesis. Any questions? Any questions so far? All right, so we can have a break for 10. We come back, discuss the lipid and protein metabolism, and this is going to be the those going to be the last two topics that we're going to be discussing today, along with some homeostatic imbalances related to the metabolism. All right, so any questions before we go to the break? Any questions before we start the break? All right, great. We'll see you in 10. Right, welcome back. Can you hear me clearly? Oh, great. For the lipid metabolism, each gram of fat actually is going to be yielding almost double the amount of energy that can be produced from a gram of carbohydrates or a gram of proteins. So each gram of lipids is going to be yielding around 9 calories compared to the carbs and proteins going to yield less than half this amount of calories is going to be around 4 calories. We use calories for kilocalories. We don't usually say a caloric number, we use kilocalorie. So whenever we say calorie, we mean by this, it's a kilocalorie. Most products of fat digestion is going to be transported in the form of chylomicrons. Please review the posted videos for the digestive system that I've posted yesterday on the Facebook group. All right, so what we've discussed in those videos, one of the topics that we've discussed was how do we absorb fat? And the absorbable form of fat is going to be either glycerol or fatty acids. Those are the absorbable forms of the fats that we are ingesting. So if this is my small intestinal lumen, and this is one of my intestinal cells. In order for me to absorb a nutrient, what I mean by absorption, it means simply that you're going to be allowing the transport here of the nutrient from your small intestinal lumen, the brush border on here, to your blood. How this takes place when we're dealing with fats, like the absorbable fat, which is the glycerol and fatty acid. We will not be allowing the transport directly to the bloodstream. We will use the lymphatic vessels to transport the fat first. And then from the lymphatic vessels, we're gonna get them delivered to the blood. So this is not a blood vessel, this is a lymphatic vessel. How we're gonna be transporting the glucose, the glycerol and fatty acid, remember, I need to transport them first through the brush border, through this cytoplasmic membrane of the intestinal cell, and then from the cytoplasmic membrane forming the base of the cell. So the glycerol and fatty acids, as they are lipids, they are lipid soluble, so they can travel through the phospholipid bilayers. They don't have a problem here traveling through the phospholipid bilayer. So the transport here is going to be taking place by simple diffusion. So the fatty acids and glycerol are going to be passing by simple diffusion. from their high concentration gradient in the intestinal lumen to their low concentration gradient within the intestinal cell. But remember, the glycerol and fatty acids are lipid soluble, but they are not water soluble. So you can't get them transported to the fluid, either the lymphatic fluid or the blood, the plasma. They can't get transported directly to water because they are not water soluble. They are hydrophobic. So in order to make them more water soluble, what we're going to be doing, we're going to be transforming this absorbable fats, the glycerol and fatty acids, into a neutral type of fat called the triglyceride. And the triglycerides are formed of one glycerol attached to three fatty acids. But this is still not water soluble. So we're going to do another thing to those triglycerides. We're going to add to them proteins, which would have charged parts, which will make them more water soluble. So we're going to be forming large complexes of triglycerides attached to proteins. What do we call all this structure formed of triglycerides and proteins attached to them? We call them chylomicrons. But those chylomicrons, they have water-soluble particles, which are the proteins that we did just add. We do have fat-soluble particles, which are the triglycerides. So can I travel through the plasma membrane now? Remember, you can't pass through the plasma membrane if you are water-soluble. So what we're gonna do with this, with those chylomicrons, we're gonna be allowing them to be released from the intestinal cell into the lymphatic circulation by exocytosis. So we're gonna be storing the chylomicrons, triglycerides, attached to proteins. They are stored in vesicles, and those vesicles need to be fusing with the cell membrane to release the chylomicrons to the outside. So we're going to get the chylomicrons on here. Again, not directly to the bloodstream, but to the lymphatic circulation. And then those chylomicrons going to be transported later on to be broken down in the liver and the adipose tissue cells for you to store those triglycerides into your adipose tissue cells. So again, how did we absorb the fat? The absorbable form of the fat is going to be the glycerol and fatty acids. And this is going to be requiring you to have lipases, like the pancreatic lipase, the lipases released from the brush border. You're going to need to have emulsification of the fat taking place by the bile in order for you to reach those absorbable forms. And again, once you get glycerol and fatty acids into your small intestinal lumen, they will pass by simple diffusion into your intestinal cell. inside the intestinal cells, what we're going to be doing in order for them to be transported out of the intestinal cells to reach the circulation for them to be distributed to the different body cells, you're going to be adding three fatty acids to the glycerol, forming triglycerides, and you're going to add proteins. All those large complexes are called the chylomicrons. And the chylomicron is going to be released out by exocytosis, not directly in the bloodstream, but in the lymphatic vessels, in order for you to reach the blood later on. All right. Questions? So we've got here the chylomicrons that are going to be released in the lymphatic circulation. Now they did reach the blood vessels, and they will be broken down by the endothelial enzymes into fatty acids and glycerol that will get them stored in your adipose tissue cells. So what if I have low energy reserves? I have low ATP in my cells. What will I do? I don't have enough ATP, so I need to break down the stored fat to produce ATP. So I will go hi, adipose tissue cells, can you please give me some of the stored energy in the form of fat? So the fat cells will do what? Will start to break down and release the triglycerides which are stored inside. So I did release the triglycerides, which is a neutral fat. Remember, this neutral fat is formed of a glycerol attached to it. How many fatty acids? I'm called triglyceride. How many fatty acids you have attached to the glycerol on here? 3 fatty acids. Great. And this will be the initial step in order for you to break down the fats, the lipolysis. So you're going to be breaking down the triglycerides into glycerol and fatty acids. This glycerol is going to be transformed into one of the intermediates of the glycolysis called glyceraldehyde phosphate. So remember, what was the glycolysis? The glycolysis was the transformation of the glucose into pyruvate. And remember, this is not a single reaction. Those are many reactions that will be taking place in order for this to happen. So one of the intermediates of the glycolysis is called the glyceraldehyde phosphate. This is the form that you will be transforming the glycerol in. So we're going to be transforming the glycerol into glyceraldehyde phosphate. Glyceraldehyde phosphate, once I've got it, it's going to be able to produce pyruvate or pyruvic acid. Pyruvate is going to be broken down, as we've seen with the glucose, into acetyl-CoA that passes in the Krebs cycle, and it's going to be releasing, if you remember, each pyruvate is going to be releasing how many NADH? How many NADH? Do you remember? Each pyruvate, if I'm starting from a pyruvate, how many NADH would I be producing? 4 NADH, remember, and 1 FADH. Producing 4 NADH, 1 FADH. Remember, each pyruvate did have how many hydrogens? Did have 5 hydrogens. All right. What you're going to do with this hydrogen attached to the hydrogen carriers on here They are going to be passing through the electron transport chain, producing 2.5 ATP from each NADH and 1.5 ATP from each FADH. So can you calculate those ATPs for me from the glycerols that you get here? So you've got 4 times 2.5, 10 plus 1.5, going to be around 11.5 ATP. This is from the pyruvate. Coming from where? Coming from the glyceraldehyde phosphate that is coming from the glycerol released from the triglycerides mobilized from the adipose tissue cells. So you've got 11.5 ATPs on here. How about the fatty acids? How about the fatty acids? Fatty acids going to pass through a reaction called the beta oxidation, and each of them going to be transformed into an acetyl-CoA. What happens to the acetyl-CoA again? It passes through the Krebs cycle, and from the Krebs cycle, you're going to be generating the NAD-FADH that will be then yielding ATPs, producing ATPs passing through the electron transport chain. So how many ATPs would I be producing from each acetyl-CoA? Can you remind me how many NADHs would I be releasing from each acetyl-CoA? How many NADHs would I be producing from each acetyl-CoA? You remember? Pyruvate did have how many hydrogens? Did have 5. It lost 1 to become acetyl-CoA along with a carbon. So I've lost 1 hydrogen, 1 carbon to become acetyl-CoA. So each acetyl-CoA is going to have 4 hydrogens, unlike the pyruvate did have 5 hydrogens. So acetyl-CoA is going to be releasing 3 NADHs and 1 FADH. If you remember, in the electron transport chain, each NADH is going to be yielding 2.5 ATP. Each FADH is going to be yielding 1.5. So how many ATPs would you be producing from each acetyl-CoA? 3 times 2.5 equals to 3 times 2.5, 7.5, and 1.5 is going to be 9 ATPs. So from each acetyl-CoA, you're going to be yielding 9 ATPs. From each pyruvate, you're going to be yielding 11.5. So how many ATPs can I produce here, knowing this, from a triglyceride? About how many? You've got 9, you've got 11.5. So how many? From a triglyceride, from a triglyceride, what do you think? From a triglyceride, how many ATPs? Remember, how many fatty acids do you have per triglyceride? 3. 3 fatty acids, and each fatty acid is going to be yielding 9. And how many glycerol do you have for per each triglyceride? You get only one glycerol. So plus 11.5. So what's going to be the number on here? 27 plus 11.5 is going to be 38.5. Exactly. All right, so you see on here, fats are going to be yielding much more energy than carbs. So again, what we're looking at in here, we're looking at how do we produce energy breaking down the triglycerides by lipolysis. We did mobilize the triglycerides, the neutral fat from the adipose tissue cells. Triglycerides are going to be broken down into glycerol and fatty acids. The glycerol is going to be transformed into glyceraldehyde phosphate. Fatty acid is going to be transformed into acetyl-CoA. Then both will be passing through the Krebs cycle to produce the ATPs that I need in my cells by allowing their hydrogen to travel through the electron transport chain. Any problem? Any problem here? All right, great. What if I do have a lot of energy and I'm eating more than what I need? So I have extra intake of carbs, extra intake of amino acids even, or extra intake of fats. I'm not using those ones to produce energy because I already have enough energy in my cells. Remember, if you do have ATPs, if you have high energy reserves, what's going to happen? You're going to be stopping the electron transport chain. You're going to be stopping the Krebs cycle reactions. You're going to be accumulating acetyl-CoA, preventing any further beta oxidation to take place. And you're going to be transforming the acetyl-CoA into fatty acids. Also, you're going to be, while you are breaking down the glucose into pyruvate, you're going to stop the transformation of the pyruvate into acetyl-CoA. And as you build up more pyruvate, the pyruvate going to be building up the glucose. Again, if you do need glucose to build up the glycogen, but in most of the cases, you will not be building up the glycogen, but you're going to be building up fat that gets stored. So the pyruvate going to be transformed into glyceraldehyde phosphate that will then be transformed into glycerol. And you've got the glycerol, you've got the fatty acids, so you're going to be binding them together to build up triglycerides, the neutral fats, that will then be stored into your adipose tissue cells. So here, if I have excess energy, regardless of the source of the energy, why am I getting fat although I don't eat any fats? I don't use any oils, I don't eat any butter, cheese, so I only eat sugars, let's say, or even proteins. If the proteins you're eating are not going to be required for your cells to build up protein structures in your body, You're not exercising, for example, but you keep drinking protein shakes. So what you're going to end up with, you're going to be ending up with breaking down this protein to generate energy. But actually, you don't need energy. I have enough ATP in my cells. So what's going to happen, this ATP is going to be building up in my cells, blocking any further Krebs cycles to take place, conversion of the pyruvate, conversion into acetyl-CoA. I'm building up a lot of acetyl-CoA, so what's going to be the reactions that will be taking place as you're building up pyruvate and acetyl-CoA, you're going to be allowing lipogenesis to take place. Again, pyruvate is going to be turning into glyceraldehyde phosphate that will then turn into glycerol, and the acetyl-CoA is going to be building up fatty acids. You're going to be binding the glycerol to the fatty acids to build up triglycerides. And those triglycerides are going to be stored in your adipose tissue cells. Slower metabolism, some people will have slower metabolism because of deficiency of some hormones like the thyroid hormone, for example. So if I have low thyroid hormones, what's going to happen? I'm not inducing the electron transport chain to take place. So I'm building up acetyl-CoA, I'm building up the pyruvate. If you have a block in here at this point in the electron transport chain, everything is going to be building up. So the pyruvate, the acetyl-CoA are going to build up, and so the glycerol and fatty acids forming triglycerides. That's why obesity is common if a person is having low thyroid hormone. I believe this is what you've meant, Martina, by slow metabolism. Yes. All right. All right, so all of you are hearing about keto diets, and some of you do also hear about Atkins diet. So how come you're saying that even if I'm not eating carbs, I can still form triglycerides that will get stored in my fat cells? Although Atkins diet or keto diet, if I am not eating any carbs and I'm eating fats and proteins only without carbs, I would be losing weight. And I've tried this and it works. How come am I losing the protein? Means I'm breaking down my stores, although I'm eating fats, proteins, even beyond my needs. I eat all I can of the fats and proteins, and I still lose weight if I'm not eating carbs. The key here is in the initial step of the Krebs cycles. One of the initial steps of the Krebs cycle that we've mentioned, remember, in order for me to start this cascade of reactions was to bind the acetyl-CoA to what, if you remember? Oxaloacetic acid, oxaloacetate. Where do I get originally the oxaloacetate from? It's coming from the carbohydrate metabolism. So the key here for Atkins diet is that if you're not eating carbs, what happens? You don't have oxaloacetate. And if you don't have oxaloacetate, would you be able to use this acetyl-CoA coming from proteins, coming from fats, to produce energy? What do you think? If I don't have oxaloacetic acid, would I be able to build up those ATPs? No. Why? Because simply you won't be able to get the acetyl-CoA to pass through the Krebs cycle, so you will not be generating the NADH, the FADH that will be passing into the electron transport chain to produce the ATP. So if you fail to get the acetyl-CoA to pass through the Krebs cycle, you will not have those protons attached to the proton carriers or the hydrogen carriers. And so you won't have electron transport chain, and as a result, you're gonna have low energy. And what your body will do in case of low energy, it's gonna go and again, knock, 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 triglyceride, fat cells, we need energy. I have low energy in my cells, so can you please mobilize some triglycerides for me? So we'll mobilize some triglycerides for you. You are reducing your energy stores in the fat cells, and as a result, you're going to be losing weight. What happens to those triglycerides again? They will be broken down into glycerol, they will be and fatty acids, and those glycerol and fatty acids will build up pyruvate, will build up acetyl-CoA. So I'm forming a large pool of acetyl-CoA. Can I get this acetyl-CoA into a Krebs cycle? What do you think? If I'm not eating any carbs, you still can't, because you don't have oxaloacetate. And if you don't have oxaloacetate, what's gonna happen? You're still gonna have low ATP in your cells. So what you're gonna do? Knock, 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 fat cells, we need more energy, mobilize some triglycerides. It mobilizes the triglycerides, you break them down, glycerol, fatty acids, you end up having acetyl-CoA. Can I get this acetyl-CoA into Krebs cycle? Still not. I don't have oxaloacetate. So what will I do? I kept building up acetyl-CoA. Can I go back and store this acetyl-CoA as fat? Can I go back? If I do have low energy in my cells, I can't go back. So I can't allow lipogenesis to take place even if I have very high acetyl-CoA in my cells. If I have very high acetyl-CoA in my cells, I still won't be able to form new fat, new triglycerides. So I can't go forward, I can't go backwards. So you've got acetyl-CoA, it can't be broken down through the Krebs cycle because you don't have oxaloacetate, and you can go back to form triglycerides because you don't have energy. I have low ATP in my cells. So what will I do in this case? The other pathway for this acetyl-CoA is going to be to become a ketone body. I will allow ketogenesis in the liver because my brain can use ketone bodies to produce energy. So I can't go forwards and I can't go backwards. The only other pathway for me is to form ketone bodies. And remember, ketone acids, ketone diet. This is a concept on here. So with very strict Atkins, which are not eating any carbs, this might cause ketoacidosis. And some people will lose their lives due to the accumulation of large amounts of ketone bodies in their system, causing metabolic acidosis. This is the same concept with starvation. Why starvation will kill you? Because simply you're gonna be accumulating lots of keto acids in your system, and this will cause metabolic acidosis that your body can't tolerate and will disturb all the metabolic activities of your cells. So you see on here, strict Atkins. Even when you go to Walmart or any grocery store, you will see those frozen meals and meal bars that says Atkins. Those are not strict Atkins, so they are not carb-free. Even when you look at the label in the back of the snack or the meals that you're getting, you will see that they still have some carbs to keep the acetyl-CoA going forward to produce some energy. It's a low carb. So rather than carb-free diet, we are moving towards low carb diet. So is the modification here that take place to Atkins diet, because Atkins is so dangerous. It can result in metabolic acidosis by accumulating keto acids. Another thing, it's the same exact concept of why especially type 1 diabetic patients gonna have diabetic ketoacidosis. Remember, if especially type 1, what is my problem? I'm not producing insulin, if you remember. And if I'm not producing insulin, would my cells allow the glucose in? Would I form the glucose transporter, the GLUT? If I don't have insulin, would I allow the glucose in? What do you think? Anybody? No. No. All right, so if you are not allowing the glucose in, this means you will not be getting the oxaloacetate, and so you're gonna have the same exact problem. You're gonna be stuck in here, and that's why you will see people with diabetes, they are losing weight. For example, type 2 diabetic patients, they most likely gonna have some degree of obesity, so they are overweight. But after they develop diabetes, you will see that they are eating a lot, but they are still losing weight. Why would they be losing weight? Because most of the glucose they are taking is going to be remaining in the bloodstream and will fail to get into the cells because they don't have normal receptors for the insulin. So they have low energy reserves, which will make them hungry all the time. They have polyphagia, and they will be losing weight because they rely mainly on breaking down their fat stores to generate the required energy needed by their cells. Any problem here with the lipolysis and the lipogenesis? Any questions? Any questions? All right, great. So moving on to the protein metabolism. The dietary protein, if it was in excess, the amino acids going to be oxidized to produce energy, or if you don't need energy, they will be oxidized and stored in the form of fat. So there is no point for you to eat protein bars to get larger muscles and to drink protein shakes to get larger muscles if you do not train. Because if you do not train, your cells will not need the protein, and it's going to be an extra energy intake that either will be used by the cells, but if you do have more energy than what you need, so this energy is going to be transformed by the lipogenesis that we've just seen into fat stored in your adipose tissue cells. All right, so how would I be using those amino acids? A very simple way to think about the amino acid metabolism. Try to imagine here, this is an amino acid. It has a carbon-hydrogen-oxygen chain that has a specific group. But each of those amino acids is gonna need to have an amine group, like this. We have 20 different types of amino acids in our bodies. And the difference between those different amino acids is going to be this group on here on the amino acid. So they all share the carbon, hydrogen, oxygen chain backbone on here and the amine group. This is common. If I did remove the amine group in here, this is going to be the keto acid of this specific amino acid. So if I remove the amine group from an amino acid, it's going to be its keto acid. The key here is that this process, this is a carbon, hydrogen, oxygen chain that I will deal with as if it was a glucose. So I will break it down. I can transform it into acetyl-CoA. I can get it in the Krebs cycle. I can transform it into fat, like what we've seen. But the key here is that this deamination process can be taken place in mainly one amine group or one amino acid, I'm sorry. This deamination. This deamination is taking place only for one amino acid. So how many amino acids I cannot deaminate? 19. So what will I do? Like all the proteins are formed by the whole package of 20 amino acids. So I have 20 amino acids building up my proteins. So what would I do with the rest of them? So what would you do here is so simple. So you're gonna have the carbon, hydrogen, oxygen chain of the one of the other 19, whatever this one is. And it has an amine group on top of it, like this. You're gonna come with your keto acids of the ones that you can deal with. And you're gonna be transporting this amine group from this amino acid to this amino acid, to this keto acid. We call this as a transamination. So what I did here, I bring the keto acid, I transported the amine group from the amino acid I want to break down to the one I can actually deaminate. So now I've got the amine group attached to the one I can deaminate. So I will be performing the deamination and restoring my keto acid. That will be going back to recapture an amine group from a different amino acid and then come back to become deaminated and so on. Is this clear? Is this concept clear? So just make sure that you got this here. This is called alpha ketoglutarate acid. This is the ketone body or the keto acid of an amino acid called glutaric acid. In order for me to break down any other amino acid, what will I do? Any other type of the 20 different types of amino acids. They are different in terms of the R group. They have an amine group attached to them. So what we're gonna do, we're gonna be transporting the amine group from the ones that I want to break down. This is the other 19 amino acids. So when I transport the amine groups, this is called the transamination. So the amine group now is binding to the alpha ketoglutarate acid. And it's not binding to my initial amino acid. So what you're gonna do with this keto acids that you get formed by removing the amine group, you're gonna be breaking it down. Each one gonna has its own reactions, but all of them gonna end up passing through the Krebs cycle. And from the Krebs cycle to the electron transport chain to the oxidative phosphorylation to produce ATP. What if I do have lots of ATP in my cells? I don't need this energy. So what we're gonna do, you're gonna be blocking here, blocking the Krebs cycle. This is gonna build up acetyl-CoA. This is gonna be building up glyceraldehyde phosphate, if you remember, and coming from the pyruvate. And remember, glyceraldehyde phosphate will become glycerol, and the acetyl-CoA will become fatty acid. You add both together, you form triglycerides stored in your adipose tissue cells. So either you're gonna use them to build up ATP, or if you don't need ATPs, they will be stored in the form of fats in the adipose tissue cells. This is a transamination. When would you do this? Is this what you're asking about, Mary? Is this what you're asking about? When would I be doing this? The transamination of an amino acid, it takes place if you do not need this amino acid anymore. So I don't need the amino acid to build up any specific protein. So I'm not exercising, I'm not working out. So I'm not gonna be in need of those amino acids anymore. So I can just store them in the form of protein because I don't need to produce any protein. So we're gonna need to break them down, and this is gonna be releasing a net gain of energy, either in the form of ATP or they will be stored in the form of fat. Transamination on here. After it did take place, now the alpha ketoglutarate acid is not alpha ketoglutarate acid anymore. It's called the glutamate. It is the amino acid or glutaric acid or glutamate. This is the amino acid I can perform a deamination for. For me to restore the alpha ketoglutarate acid again. will get back my alpha ketoglutarate acid that will be ready to recirculate and pick up another amino acid later on. So this deamination results in the release of ammonia that will become the urea that would be filtered out in the nephrons and released out in the urine. So two very important steps on here in the metabolism of the amino acids. You have to perform transamination followed by deamination. Why do I need transamination in the first place? Because my body has the enzymes that are capable to perform an oxidative deamination only for the glutamic acid. Again, oxidative deamination, when it takes place, you're going to get rid of the ammonia, the amine group, and this is going to be losing carbon. You're going to add to it carbon dioxide to become the urea, which is much better to become soluble in the blood, and the urea will be released out in the urine when you filter your blood. Questions? All right, so what we're gonna be doing if we need proteins. If we need proteins, we need to have a complete set of amino acids. And not all the amino acids can be produced in your body, so you need to get them with your diet. So we call those amino acids that needs to be ingested, those are the essential amino acids. And in order for me to produce a protein, it needs to be a complete, I need to have a complete set of those amino acids. Protein synthesis is going to be hormonally controlled. So to build up a protein, you need to have the signals from your genetic code that encodes the formation of this specific protein. Moving on to the metabolic states of the body, we have the catabolic and anabolic steady state, which is the continuous breakdown and rebuild of the organic molecule, except for the DNA. So you are building up and breaking down carbohydrates, fats, and proteins all the time. So you have an interconvertible nutrient pool. So whenever I need protein, I can break down the amino acids, I can break down the fats to build up my carbohydrates. And remember the production here of the carbohydrate from a non-carbohydrate source, glucose from a non-carbohydrate source is what we call the gluconeogenesis. I can break down the carbs into fat if I have extra intake of carbs. I can build the non-essential amino acids and so on. So I have those interconvertible nutrient pools that will be sharing in the formation of the catabolic anabolic steady state. The absorptive or fed state, this is the short period after I'm done eating. And this is a time when you're going to be performing the absorption of the nutrients. So you're going to have high glucose, high fat in your blood, high amino acids. So if I have lots of glucose, lots of fat, lots of amino acids, it's time now to have reserves. So this is gonna be inducing the anabolism. So the anabolism in this state is gonna be exceeding the catabolism. So you're gonna be using this glucose to build up the glycogen. You're gonna be using the triglycerides, the absorbed fat to build up the triglycerides into your fat cells. If you want to build up muscles, for example, or to build up enzymes, or to build up carriers, or whatever you need as proteins, you're going to be using those amino acids to build them. And if not, if you don't need them, you're going to be breaking them down and store them as fat and glycogen. So here in the fed state or the absorptive state, I will be inducing mainly anabolism. Anabolism in this case is going to be exceeding the catabolism. The hormones that's going to be released in this case is going to be the insulin. Remember, when I have high blood sugar levels, my pancreas will be inducing the release of its induced to release its insulin out for it to enhance the cells to absorb the glucose. What if it has been a while that I didn't eat? So now my gastrointestinal tract is empty. I don't have anything in my small intestines to absorb. So what happens to the blood glucose levels? Blood glucose levels gonna be dropping. So it's time now to induce catabolism. It's time now to break down my stores. And if you remember, the hormone that induces the catabolism in case of drop in your blood sugar levels, in order for it to maintain the blood sugar at normal levels, is going to be the glucagon. And if you remember, the glucagon was another hormone produced by the pancreas that induces the catabolic reactions. If you remember, this was enhancing the gluconeogenesis to take place in the liver. It was enhancing the glycogenolysis, the breakdown of your glycogen in the liver and muscle cells. Also, the catabolic reactions here are going to be induced by the sympathetic nervous system, which going to be mediating its effects by the epinephrine that promotes mobilization of the fat and glycogenols. The energy in your body is kept in balance. The energy released from food that you're taking is going to be equal to the energy output. So what are the forms of energy output? We have an immediate energy loss in the form of heat, around 60%. We have the actual work that we are going to be producing, and this is going to be mediated by ATPs. And any extra energy intake that you will not be using to work and will not be lost as heat, it's going to be stored in the form of fat and glycogen. But mainly, remember, mainly fat. It's much easier for your body to build up fat than to build up glycogen. So if the work and heat together are equal to my energy intake, so the intake is equal to the energy output, my body weight will remain stable. So I will have stable body weight. If I have excess energy intake beyond my needs, all the extra energy gonna be shifted and get stored in the form of fat mainly, and to a less extent glycogen. So if a person has a higher energy intake than energy output, what's gonna he end up developing? He's gonna end up developing obesity. How do we diagnose obesity? By checking the body mass index. And this is something that you're gonna be completing in the metabolism lab handout. So you're gonna be measuring your weight, checking your weight, checking your height, and you're gonna use this equation here to check your body mass index. A person would be considered overweight if his body mass index is falling between 25 to 30. So the equation here is your weight in pounds times 705 over your height in inches square. Or if you are familiar with the metric system, it's your body weight in kilograms divided by your height in meter square. So kilogram over meter square. All right, that's going to be if you're using a metric system. Considered obese if the body mass index is greater than 30. We have multiple levels of obesity, as you will see looking at the metabolism lab handout. What is the problem with obesity? The problem here is that I will be dealing a lot with fats. And if I'm dealing a lot with fats, so I have a lot of fat circulating in my vessels, this puts me at a great risk of accumulating the fat in the wall of the vessels, developing atherosclerosis. Also, it's gonna be a risk factor for the development of chronic diseases like diabetes and hypertension. Also, narrowed vessels will increase the risk of developing myocardial infarctions and other heart disease. Also, having extra pounds will put more weight and stress on my joints, which will cause the inflammation and the destruction of my cartilage and irritation of the bone. This is what we call osteoarthritis. If you remember back from AP1, when we studied the brain, and back when we studied the water intake, remember the part of the brain that is responsible for the regulation of all those automatic activities is going to be the hypothalamus. In the hypothalamus, if you remember, the part of the hypothalamus that was responsible to regulate the water intake was the hypothalamic thirst center. Here, the part of the hypothalamus that is responsible to regulate the food intake is going to be the arcuate nucleus. Other brain centers also going to be involved in regulating the eating behaviors. Factors that will be involved in food intake, this includes neural signals from the gut to the brain, nutrient signals, and in order to understand this, so if you are willing to limit your food intake and you have a cake, you are attending a birthday, and you've got a cake. Which one is going to be easier for you to just eat a small piece, just a small piece of the cake, or to not eat any of it? Which one is going to be easier for you if you are trying to limit your food intake? The urge for you to eat, will it be increased by eating a small piece or not eating at all? Small piece, if you did eat small piece, is going to be much more difficult. It's going to be much more difficult for you to stop getting more. So what happens? When you eat this piece of cake, what's going to happen? You're going to be absorbing glucose. And who loves the glucose? Your brain. Your brain loves the glucose. It's the best source of energy for the brain. So having this glucose surging in your blood delivered to your brain will get, I need more of this. So you will find the urge for you to eat more of it has increased if you did eat small piece. So rather than getting something like this, you might replace it with something else that will be slowly giving the brain glucose, not a sudden surge of glucose in your blood that will make your brain so excited about getting more. Fruit is going to be a better alternative, but is not the best. Honey also is not going to be the best thing. Uh, so complex sugar, yes, like whole bread, for example, whole bread. So fruits, honeys, those are high in caloric content and in sugar levels. Are they definitely going to be absorbed much slower than the sugar in the cake? You're going to have a slower absorption, but definitely it's not the best thing. All right, if you are trying to lose weight, for example. Yeah, just stay away, exactly. All right. Plasma concentration of hormones, and you definitely see children by the age of puberty, they will be eating much more than what they are used to because of the sudden rise of the sex hormones. So you're building up more uh, more cells, you're growing fast. So this surge of the hormones is going to be inducing the more food intake. Body temperature, if you notice, you tend to eat more during colder weather. So during the winter, for example, you will find yourselves that you're eating more, and you will not figure this out until the summer comes in and you're gonna be getting your shirts out for the summer, your clothes out, and you will find, yeah, they are not fitting anymore because simply over the winter, your food intake was greater than during the summer. So a lot of people will be experiencing that they have gained weight over the winter. Also, definitely psychological factors affect food intake. All right, so in order to get, for example, if a person is not feeling well, he will tend to eat more just to give to get a good feeling as a feedback from the brain to this high sugar levels. And this is something that will be definitely prominent during this lockdown. So a lot of people are not feeling well because of the lockdown. They can't socialize, they can't go out as they are used to. So people now are going to be having much more food intake. Also, lacks of sleep and cortisol. Cortisol acts in a different way rather than increasing. It slows down the metabolism. It slows down the breakdown of the fats. So it rather breaks down proteins instead of fats and increases the blood sugar levels. This is what happens in case of uh, high cortisol levels. So I'm breaking down more proteins to build up glucose that I'm not using. So this high glucose is going to be stored in the form of fat. In case of stress, cortisol is going to be, yes, definitely increasing the body weight. But here it doesn't have a major effect on the food intake. All right. It mainly acts by slowing down the metabolism and inducing the formation of glucose that if you don't use, it's going to build up and stored in the form of fat. All right. Questions? All right, great. So metabolic rate is going to be measured. It's the total energy used by the body per hour. The basal metabolic rate is reported as kilocalories per meter square, which is the body surface area, and this is measured per hour. What is the basal metabolic rate? This is the minimum amount of energy required for your body to drive the essential body processes, for you to breathe, for your heart to contract, for you to keep your skeletal muscle tone, for you to rebuild your tissues, for your lungs to inflate, deflate, for you to, for example, maintain your posture. All those are going to be taking place even if you are sleeping. So all those activities going to need energy. In order for me to just perform a partial contraction of my muscles, this requires ATP to maintain my muscle tone. So this amount of energy required by your body is what we call the basal metabolic rate. And this is one of the things also that you're gonna learn how to calculate when you complete this metabolism lab handout. What are the different factors here that will be affecting my basal metabolic rate? The ratio of the body surface area to volume. So if the ratio of the body surface area to the volume increases, the basal metabolic rate increases. What does this mean? So if you will have a person who is taller, who has a much larger body form, so he has a much greater body surface area, he tends to lose weight faster than a person who has a short stature, a smaller body surface area. So having a higher body surface area, larger body form will be a major factor here in determining the basal metabolic rate, which is the energy required to just sustain the essential body activities. Also, age. As a person gets older, the muscle bulk is going to be reduced. So the energy required for the muscle tone to be kept is going to definitely go down. Also, all the body activities going to be slowing down as a person gets older. So this will be reducing the basal metabolic rate, again, energy needed for me to maintain the essential body activities. Increase in temperature, increases with temperature. If I did have an increase in temperature, basal metabolic rate slightly goes up. And this is the concept why people do go to sauna, for example. So it's not much, doesn't have a much contribution, but some studies did show that higher temperatures tend to increase the basal metabolic rate. Also, in case of stress induces the release of stimulation of the sympathetic nervous system, and so the release of the epinephrine or the adrenaline. And remember, this epinephrine is going to be a catabolic hormone. That will be breaking down the stored fat to increase the glucose. Increases the heart rate, increases the respiratory rate, increases the blood pressure. All those are going to be increasing my energy needs to sustain the basic activities, inducing the basal metabolic rate. Same, it's going to be here for males. Males will have a higher basal metabolic rate compared to females, mainly due to the higher muscle bulk. Thyroxine increases the oxygen consumption, cellular respiration, and the basal metabolic rate. Diabetes, if you remember, we have two types. We have type 1, which is going to be a problem with the formation of insulin. We have type 2, which is a problem in the insulin receptors. So my problem here is that I'm not able to get the glucose to the inside of my cells because I don't have the glucose transporters. Because either I don't have insulin or I have an abnormal insulin receptor. So if you're not able to get the glucose into the cells, so this glucose is gonna remain high in your bloodstream. And if it remains high, remember, glucose is not a plasma protein, it's not a macromolecule, and it's not a cell. So those are the three things. If you remember, back when we studied the kidney, those are the three things that you're gonna be preventing the filtration of. So you can't filter those three things. Glucose is not one of them. But remember, yes, the glucose gets filtered, but it also gets reabsorbed If you remember, in the proximal convoluted tubules at normal blood glucose levels, what was the percent of the glucose that you get reabsorbed? You remember? 100%. All the glucose is going to get reabsorbed. What if I have a very high blood glucose levels? So a lot more glucose gets filtered. And this will exceed the ability of my receptors to allow all this amount of glucose to get reabsorbed. So not all the glucose now is going to be reabsorbed. So some of it going to remain in my filtrate and will get secreted with the urine. So we're going to have this high blood glucose levels causing glucose release in the urine. This puts a patient at a risk, if you remember, of developing metabolic acidosis. Why do I develop metabolic acidosis again? Because I am accumulating acetyl-CoA. I can't keep going forward to break it down through a Krebs cycle to generate the energy. Why? Because I don't have oxaloacetic acid. And glucose is going to be required for me to get this oxaloacetic acid. So I can't go forward, but I don't have energy in my cells. And if I don't have energy in my cells again, I have low ATP, I can go backward to store this acetyl-CoA in the form of fatty acids. So I can't go forward, I can't go backward. So the only other pathway for me is going to be to transform this acetyl-CoA into ketone bodies. And so ketone bodies accumulation going to be the reason why those patients are at a risk of developing metabolic acidosis. More severe conditions will, if the blood sugar is not controlled, can result in coma and death. Other homeostatic imbalance that we're looking at today is going to be the high cholesterol. The circulating fat has multiple forms. I have the best one that I would like to deal with all the time is going to be the high density lipoprotein. It's less likely to deposit in the wall of my vessels compared to the bad one that is going to be high in cholesterol. It's going to be the LDL, the low density lipoprotein. This is the bad guy who tends to deposit in the wall of the vessels. And this is going to be the greatest indicator here of having high cholesterol. Having an increase in the LDL levels puts me at a risk of developing atherosclerosis. And as a complication of atherosclerosis, if I have narrowed coronary vessels, this is going to cause other cardiac problems. So your body doesn't tend to keep anything higher than normal more than the LDL. So most likely, because it's like a cycle. So if you go to the cholesterol metabolism, and you will see that the point that most likely a person with higher cholesterol will be stuck in is going to be in the LDL form. All right. It's the high density lipoprotein. If it was high, It simply means the fat intake is higher, but it carries less risk than the LDL. Still needs to be monitored, still needs to be worked on to get it reduced. But fat intake, yes, and obesity, and a person being overweight, yes, all those are risk factors for an increase in the circulating fat. All right, fat intake is one of them. Also, obesity is another risk factor, and overweight, generally speaking, even if it's not obesity. Some genetic problems can contribute in higher levels of circulating cholesterol. So we have multiple diseases that can contribute. So this needs to be investigated more. So you can't just make a decision about the patient just by having one reading. All right. If you want, we can discuss the steps of the cholesterol metabolism after we're done today. All right. So how do I reduce the risk? How do I reduce the risk for atherosclerosis if a person has high low density lipoprotein? First, we're gonna be trying to improve the diet. So reduce fat intake, reduce carbs, because also if you are getting lots of carbs in your diet, this extra energy gonna be transformed into fat. So improve your diet and exercise for you to get rid of the extra pounds. This is gonna be the first line of defense here that we're gonna be using to defend the body against atherosclerosis. But if the LDL, the low density lipoprotein, is gonna be above 130 milligram per deciliter, this is a number that you don't want to wait and see if the diet improvement and the exercise did solve the problem or not. At this point, if I have this high levels of LDL, I need to lower it down using medications. And the drug of choice here is going to be the statins. Those are cholesterol lowering drugs. All right. Any questions? All right, so let me review quickly what do we still have. All right, so this is gonna be our last virtual meeting that I